Is it working? All right, so now we come to the final, I think it's final paragraph. I'll try to explain how we can conclude. This is 7.7. So this is computing the quotient of the homotopy limit that you are interested in. Okay, so let me remind you what we have. So we have a map from the homotopy limit of the Čech complex on the spectrum representing the Ram cohomology. So this goes to the homotopy limit of this pi star construction on some explicit T spectrum, which is G lower star, infinite suspension of Goldman complex of some chi dot some co-simplicial complex of Flaggy presheaf, which was denoted by x dot Hodge, and this has to be made fibrant before applying G lower star. Okay, so we have this map, and now just obviously by the construction of the Bloch-Levin tower, I can go from here to a map to the homotopy limit of the associated complex of presheaf or T spectrum of the limit of the tower. So this will be homotopy limit so Bloch-Levin tower star of exactly the same thing. So maybe I don't write it. And as I also mentioned at the beginning of the lecture today, in this particular context, this A is not really doing much. It's given by a homotopy colimit, but all the transition map are quasi-isomorphism. So in fact, one can put A, one can commute A and the homotopy limit. So you can put A here. And now I have two homotopy limits, and then I also can commute them. So this will be okay. Now P is fixed, right? So now I somehow I concentrate on this guy here. So here now, so if I evaluate this at so if I fix level scheme X and evaluate what happens here for a fixed P, then I can use the criterion from the previous section, which would tell me that in fact I don't need to know that I could replace my X by anything which has the same values at these star polytray, which are which are of some special kind. Okay, so let me try to say this more precisely. So in fact, yeah, maybe it's better to do it like this. Now we also have, on the other hand, we have a filtration FD on this object. Remember, and this filtration is induced by by filtering the category A by some FD A, so for various, okay, so we remember, yeah. So there is a filtration on this category by the dimension of the target of U. Okay, and this filtration induces a filtration on these flaggy complexes of presheaves. Now if I want to compute the homotopy limit, or if I want just to compute just the Bloch-Levin tower at X, somehow the previous proposition, really the proposition from previous paragraph, tell me that in fact I can do it I can replace X by FDX for D big enough. Okay, is this clear, or should I try to explain this more? Is this clear? Okay. Maybe let me just say it once again. So if I fix X, so I can use the previous proposition and then also the previous theorem, which tells me that in fact for all the relevant, if I put here V star instead of X, for all the relevant polytray V star, we have in fact essentially equality of these two categories. Okay, because of the previous theorem, if X is fixed and P is fixed, and therefore I have now a bound on the dimension of the U which are relevant, and therefore I can use this argument from Hodge theory, which then enables me to compute the homotopy limit. Okay, so by the argument from Hodge theory, this homotopy limit for X fixed is the same as, so I can write it down. It's the Bloch-Levin tower of sigma T infinity Godman complex, and now I just replace X dot by X minus 1. Right, so this is using the ingredient from Hodge theory. Yeah, we got rid of for the homotopy limit of the main homotopy limit. Yeah, yeah. So we computed in some sense we computed the homotopy limit. Okay, so we get yeah. So let me again write it down. So we obtain, so by this reasoning we have a map from the homotopy limit of Čech omega that goes to the associated complex of presheaves or spectrum, whole limit of the tower the Bloch-Levin tower. Okay, so this is what we have, and now the rest of the argument is to try to go from here to this thing. And so this is constructed in a few steps. So that this is constructed in few steps. So try to describe these steps. Okay, so step 1. So this is replacing a chi minus 1 Hodge by a simpler complex. Okay, so let me describe to you this simpler complex. Okay, so let us recall what is x minus 1, and then I can tell you what is the simpler version. So x minus 1 Hodge takes a fourth tuple I alpha x star d, and so it sends this thing to homotopy colimit of u of basically cohomology of u circ with value in mu, some module of logarithmic type over u circ. And so what we can do, there is an obvious map to something where there is no homotopical limit anymore, and namely this is the ramp cohomology, the cohomology, I mean this is the derived global section, sorry. Derived global section, not of u, but of something which is independent of u, namely this is m circ x10 d underline, and this is with value in the logarithmic, in the module of logarithmic type n, or maybe nd. Okay, so remember mu is really just the underived direct image of nd, and there is a natural map like this. And so this is what let's call this guy here just y of I alpha x star star and t. So this is again a complex of Flaggy presheaves, and obviously I can and there is a map, there is a map from x minus 1 to y, and I can replace here this thing by y. So this is the first step. say this. So, I mean, you see much of the things are happening at 0, 1. For example, this. I mean, the construction. I mean, this pi takes into account some affine spaces which are over 0, over 1, and 1, 1. So most of the construction is happening on this side, and if you put it there, it's just too complicated. So it's better to have it on this side. And I mean, and this is used in step 2, which unfortunately I will not be able to really get into the proof. So it's maybe not clear how this is used, but it's really it's important in step 2. Sorry, say again. If there is.
Since you have a lot of construction on 1, 1 and 0, 1.
Yeah. Yeah, this is why it's I put it on 1, 0. Exactly. Yeah. Okay. So and as I said, this is the reason why you put it on 1, 0 somehow is apparent if one try to get into the proof of step 2, which is a crucial step in some sense. This is where we somehow where we close the holes in the Bloch-Levin tower. So we somehow we put back somehow the closed subset that we have removed. So okay, so let me. So I try maybe to say at least orally how this enters. So let's see. Let's fix a scheme which is leveled. So finite type. And let's work. So we work at also at level m, but level m not level m in the sense of spectra. So here's a claim. Is that for p big enough, so with respect to x and m, so for p big enough, the map in the Bloch-Levin tower, so p LP plus 1 star evaluated at x to, so the same thing is a quasi-isomorphism. All right, and so let me just very quickly just tells you what's going on here. So okay, so this boils down to so-called purity in motivic cohomology. Which is the statement that if you look at motivic cohomology, let's say in degree q, but in weight p, and you look at the restriction map to some open subset. So this is an iso if x minus u has codimension bigger than p plus 1. yeah. So we want to apply this, of course, for p equal to m. Right? So we take p. So if p is m, this is, I mean, motivic homology with value in ZP is just another notation for taking the I don't know, the étale cohomology, if you want, or the Nistevich cohomology of X with value in T tensor M made A1 étale fibrant, for example. Okay. And so and here, so at the Bloch-Levin tower at p+1, we are removing closed subset of codimension bigger than p+2. Okay, and so it's I mean, it's not surprising that to prove such a thing, it's useful to have something like this. Now, of course, this is not so simple, and one complication comes from twisting by y, right? So twisting by y somehow destroy. You cannot just twist by any complex here and hope that this is still true. But now, somehow, since y is coming, you see that there is this situation. So here we have 1, 0. Here we have 1, 1. Here we have 0, 1. So computing this, I mean, this is really something happening here, in the sense that you take an A1 fibrant replacement, maybe étale, and this is somehow only computed here. And since y is really coming from this side of the diagram, it doesn't interfere too much with motivic homology, and this is still true in somehow for this twisted version. Okay, and so this is the idea why we have this. So the Bloch-Levin tower, I mean, you can replace. I mean, you can replace this by motivic homology. You can put here if you want ZM. That doesn't matter. Now the Bloch-Levin tower, you have to remember the construction. So this was constructed by somehow evaluating at these guys, UP, right? And these are the pro-opens that you obtain by removing closed subset of codimension bigger than p+1. So this is at level. This is BLP. Here you are removing something which is of codimension bigger than p+2. And so this thing here pretty say that at some point it doesn't matter what you are removing, unless if it's of codimension big enough, it will give you the same answer. Right? So this telling us that this tower somehow stabilizes for p big enough. Okay, so what is the conclusion of this? The conclusion is that you can replace this the homotopy limit of the tower, of the Bloch-Levin tower, by the thing that comes just before in its construction. Namely, we get now a map from the homotopy limit of what we want to this version of the Suslin-Vygotsky complex. So by hat star G lower star infinite suspension chi of y HH fibrant. And in fact, since this guy is fibrant, this is also the same as just pi star. The natural map goes like this. Right, so this is step 2. Now step 3 is going back.
You did two steps in one.
Did I do this?
The first line is already removing the colimit over P.
Yes.
Is that right? This says you can remove the colimit over P.
You mean the limit over P? Yeah.
Colimit.
Yeah, yeah.
Like as if I know the difference between a limit and a colimit.
Okay.
There was a homotopy limit
Yeah.
over P.
Right.
But that goes away because for P
Exactly.
is large. So that's already one significant thing.
Yeah.
In this purity.
Yeah, yeah.
That's on the first line.
Right.
But then what did you do on the second line?
Here, you mean?
Second line.
Here.
Yeah.
Oh, this is okay. This is a lemma we have seen today. I don't know. So this is so this is essentially what you have when you go to the limit, right? So when you don't have any holes anymore.
Yeah, this is the version without holes.
Right. This is without holes. But then there are still these blow-ups.
Yeah.
Right? And this is a version without anything, without blow-ups. This is just the plain version, the simplest one. And this is a general fact. Whenever you have something which is fibrant, for the HHH topology, you have a quasi-isomorphism like this.
Oh, because it's fibrant for the
Exactly. Yeah. That gives this.
Yeah.
Okay. So, okay. Now it's step 3 is going back to. So it's a bit weird. One has to. I mean, I didn't find any way to do this. So one has to go back to foliations, and this is essentially somehow to get rid of the H topology. So again, I'll be very sketchy here and just say a few words. So here, the idea is that so by reversing some constructions. So I mean, before I was, if you remember, I had something which involved foliation, and I was spent some time to explain how one could get rid of foliation and write everything in a way which is completely algebraic. And here the step is somehow going back a little bit. So somehow it's like, I mean, there is maybe some tension. So it's either you work with foliation, and then you can have a topology which is not so bad. Or if you want to have something which is algebraic, you are forced to work with the H topology. And so somehow you cannot have both. And so yeah, so somehow this step is the goal of the step is to get rid of the H topology, and for this we need to go back to foliation. So I will not really explain how this works. I want to explain the construction of a version, if you want, of this Y. Which involves only foliation and maybe the Psi et al topology, and for which we can find a map from Y to this. All right. So let me just do this construction. All right, so consider the morphism of site that as follows. So I call it E. So let's go from smooth foliations over the diagram E bar, theta bar, omega n. To the étale site of the same guy. Okay, so I endorse this maybe with the psi étale topology. Okay, now let's see. I want to define. First, I want to define a complex of presheaves here, and then put it back here. So let's see. Sorry. Can you say again?
I didn't remember what is
FT. So these are the foliation which are differentially étale over the base. Okay, so given, so let's fix I alpha in theta bar omega n, and x over f, which is diff étale over E bar alpha. Okay, I want to associate to this some complex, which will obviously have to do with y, and without proof, I will tell you then that you can replace y by the thing here. All right. So remember that in this situation we have this associated map or quotient, universal quotient such that x is over E alpha 0. Okay, so this is the largest quotient such that the image of x in E bar alpha 0 is contained in the open E alpha 0. Okay, so right, and then we look at, so we have this torus E alpha 0, and there is also a well-defined quotient of, so this is a quotient of tori, which is again the largest one, such that if you look at E alpha 0 times AI, and you put this natural foliation structure on this, I don't know if you remember this. There is this exponential foliation which is on this product, and you look at the map projection to T. This factors through the discrete torus. Okay, so essentially, I mean, this is actually quite simple, and maybe it's a bit complicated the way I'm writing this. But so you see, yeah, essentially what I'm saying here is that if you look at the function which are in the kernel of the derivative, it will define to you a quotient which is a torus, and this is T. Okay, so there are many functions here which vanish by the differential of this foliation, and the subalgebra is just the algebra of a torus. All right, so with this, then you then set. So I define y prime, so I alpha x over f, by definition to be the R gamma delta of, so yeah, it's actually, yeah, let me not like this, this is not correct, but doesn't matter. Okay, so it's the ramp cohomology. Yeah, actually, I don't want to take R gamma. I really want to take the ramp cohomology. I don't know. Let's just write it like this: omega. The ramp complex. Yeah. Yeah. Okay. If I want to be really correct, I should do it differently. Put a T here. All right. So let me explain what this means. So so this is a spectrum of what is it? Yeah. So you take OX and you go to omega of x times T delta. Right, so you look at the function here, which are 0 in this product. So this defines to you an algebra over T, which is differentially étal, and then you tensor it with T delta. Is this correct? No, I don't think this is. No, this is not the right one. Sorry, I have to do it. Sorry, it doesn't matter, I think, but just to be correct. So what you do, you look at xf, and you take E alpha 0. Again, so this is the same thing. You look at functions over x which are constant over E alpha 0. You take the spectrum of this. So this defines to you an E alpha 0 diff étal foliation. Then you tensor this guy with T tensor T delta, and then you compute the ramp cohomology with value in alpha. Okay, so it doesn't matter at all. I just let me just state two things which really which somehow justify such a definition. So first is that we essentially still have a map. Yeah. So the right-hand side. So this is constructed in a way such that the right-hand side from this above maps to pi. Now there is no star anymore, but to pi of sigma t infinity of E upper star. Oh, there is a star. Let me put a star here. It's a star here. So this is now it's one has to work over I don't know, this part of the diagram. So we don't need any more this, but we still need so yeah. Okay, it doesn't really matter. Just let me. So we still have such a map, and the second important property is that so this guy here. So this is a foliation, and so the f dimension, so the dimension of the leaf, happens to be smaller than the cardinality of I minus 1. Okay, let me just explain this quickly. So yeah, I mean the point is that so this foliation here has dimension less than the cardinality of I minus 1, because it's differentially étal over AI, which is a smooth scheme of dimension cardinality of I minus 1. Okay, and yeah, and yeah, and by construction, I mean, in fact, this is not completely obvious, but one can show also that this guy, so the dimension of this torus of T is let's say, yeah, is equal it's alpha 0 minus the cardinality of I minus 1 plus 1. Right, so what I'm saying here is that the map from here to here, the fiber of this map have dimension at most cardinality of I minus 1. Right, so this is really a big torus. And this has to do with the reason. This has to do with the choice of omega. In fact, so if you remember omega of I, this is a set of translate invariant one forms defined over Q. Okay, so this is. If you take coordinate, this is something. This is just dt1. This is a vector space over Q, generated by dt1 up to dtn. Okay, and because of this, you see that yeah, that so if you take a big number of such differential forms, then you can write most of them as a linear combination of at most cardinality of I minus 1 of them. And because of this gives you this big torus. This creates a lot of constant, and you can show that this torus is big, and therefore we have this. So since the dimension of the fiber is bounded by the cardinality of I minus 1, and if you think about this for a moment, you see that this foliation has also a dimension like this. And in particular, this complex, y prime I alpha xf, has no cohomology in degree bigger than cardinality of I. So it's a bounded complex, and it's bounded in terms of the cardinality of I. All right, so now we are almost at the end. So these two, I mean, this property here implies the following. Sorry, this implies that this complex here is minus 1 connected. Right, so one has to look at this a bit carefully, but and one has to go back to the definition of this operation and so on. But from this boundedness of in the degree, you can check that this complex is indeed -1 connected, and then there is an obvious map to omega, and this -1 connectivity tells you that this map factors through the truncation. Right? And this gives you the map that is that you are looking for. Okay. I think this is all what I wanted to say. I hope you see what that this ends. Okay, and so.